we just gave you the definitions of Z-transform. We shall continue with that. We will see some other important properties of Z-transform. We defined Xz as sigma xn z to the power minus n varying from minus infinity to plus infinity. Z is a complex variable. Now, if xn is causal, causal means it exists only for n greater than equal to 0, all right. For n greater than equal to 0, xn exists. Okay. This is non-zero, maybe 0, but xn is 0 for all negative n. This is a causal sequence. Now, Xz is a power series that you can see in Z. It may not converge at all, it may or may not converge. So, let us investigate under what situation it may not converge. The region in which it converges we call region of convergence, or in short ROC. Okay. So, we will put the boundaries where it will be converging or it will not be converging. Let us take the following series: Xz equal to 1 plus 2 Z2 plus 3 Z3 plus 4 Z4 plus 3 Z5 plus 2 Z6 plus Z to the power 7. What is this sequence in terms of Z to the power minus 1? If we try to see, it is a sequence which exists in the negative domain of time. Okay. 0, 1, 2, 3, 4, 3, 2, 1 and then 0. So, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, this is n. Now, for such a sequence where for negative values of n only xn exists, henceforth it is all 0, the value of xz will be this. Now, does it exist for all values of z? At z is equal to infinity, xz becomes infinity. We would like to see when the function becomes infinity, that means it is not converging. When z is very, very large, as it is tending to infinity, the function xz also tends to infinity. So, the function exists except at z is equal to infinity. Let us take the similar sequence, but with a shift. Suppose we have the same sequence with a shift. Four, 3, 2, 1, 3, sorry, this is 2, 1, 0. So, minus 1, minus 2, minus 3, and then this is 1, 2, 3, 0. What will be the value of xz? Z to the power minus 3, start from here, plus 2 into z to the power minus 2 plus z to the power minus 3 plus z to the power minus Is it z to the power minus 4? It should be minus 1, yes, then 4 into z to the power 0 plus 3 into z to the power, it is plus 2 plus 1, is that all right? Now 2 into z to the power minus 2 plus 3 into z to the power minus 3. Okay. Now what are the values for which xz becomes infinity? Z is equal to 0, it becomes infinity. Z is equal to infinity, also it becomes infinity. So its region of convergence will exclude these 2 points. At these 2 points the function becomes infinity. Is that all right? If we shift it further by 4 more steps, then we will have a function like this: 0, 1, 2, 3, 4, 3, 2, 1. Okay. What will be the sequence? Corresponding sequence: z to the power minus 1, this is xz, to z to the power minus 1 plus z to the power minus 2 into 2 plus 3 into z to the power minus 3, and so on. At the end z to the power minus 7, 1, 2, 3, 4, 5, 6, 7. All right. Now when this function becomes infinity, that you have to identify, that you can see from here, when z is equal to 0. Anybody? Z is equal to 0. Okay. When z is equal to 0, xz is infinity. So a sequence that we have considered in the 3 cases is having the same nature of variation, but it is shifted, all right, from left to right, and the region of convergence also changes. Earlier it was not converging for z is equal to z is equal to infinity, then z is equal to 0 and infinity, and now z is equal to 0. So region of convergence will be depending on the nature of the polynomial, nature of the function xz that you get. Let us consider this sequence, well known step function which is 1, 1, 1 and continues. So what will be corresponding Z transform? xz 1 plus z inverse plus z to the power minus 2 and so on. It will be 1 by z inverse. It is a GP series provided z inverse is less than 1 or z is greater than 1. Okay. So the region of convergence, z is a complex quantity. So in the complex z plane, it will define a unit circle. Okay. So this is a forbidden range and this is ROC. The space outside is the region of convergence. The region of convergence is the space outside. This is real and imaginary part of Z. All right. Now for this sequence, you can see for yourself, if I put Z is equal to 2, then it is 1 plus half plus x at 2 becomes 1 plus half plus 1/4 and so on, and this is a GP series with reduced magnitude of these terms. So this will be tending to 1 by 1 minus half, which is 2. If I put Z is equal to half, then it becomes 1 plus 2 plus 4 plus and so on tends to infinity. Okay. So, any point inside, if I choose, I have just taken half, you can say choose any value, any complex value, it will be diverging. So, for a causal system, a finite sequence length, a finite length of sequence xz converges. Because you have got finite number of terms, okay, except at 0, because causal sequence means the terms will be x0 plus x1 into z to the power minus 1 and so on, all right. It will be causal sequence means it will have some value here and so on. If I put z is equal to 0, z to the power minus 1 will tend to infinity. So, all the terms will be giving you finally xz will tend to infinity at z is equal to 0. For infinite sequence, that is sequence of infinite duration, xz converges outside a circle. The circle is bounded by the pole. Okay. Pole means if it is an infinite sequence, all right, if you can resolve it in terms of some az by bz, then the roots of bz will be called poles. So, at those points, at those values, the function will try to blow up. This becomes 0 means the function will be having infinite value. So, at poles the value of the function will be infinity, all right. So, that will be excluded, the region of convergence will have to exclude those poles, all right. You must have studied in complex algebra analytic functions. So, wherever there are poles, there will be the function will try to go to infinity. So, for an analytic function you exclude those poles, is it not? For stable sequences, we have not yet defined stability. What stability? So, next we will take up stability. For stable sequences, the ROC, the region of convergence, always encloses the circle of unit radius. This point we will discuss after we define what stability is. Okay. Stability of a sequence, of a system. When we define the impulse response of a system, Hn, this dictates the behavior of the system, all right. Now, what are the conditions on Hn? What are the conditions on Hn for stability? What do you mean by a stable sequence or a stable system? If this is driven by an input which is bounded, then output must be bounded. That means, if Xn is bounded, for a bounded input sequence, if x n is bounded, then y n also should be bounded for a stable sequence h n, all right. If that is violated, then the system is unstable, all right. What is it actually telling us? It says that if I give an input sequence whose magnitude does not grow beyond a certain value, whose maximum value is limited, then the output will also have a maximum value which will be limited, which will be less than infinity. Output cannot tend to infinity. If it does, then it is an unstable system, all right. So, let us see the proof of this. Let the magnitude of x n, the maximum value, be restricted to m x. So, x n can be at the most equal to or less than m x. Now, y n is sigma x k, okay, x n minus k into h k, is it not? So, y n magnitude will be less than or equal to magnitude of x n minus k into magnitude of h k. Do you all agree? It has to be less than the product of the two magnitudes and then summated. So, that means it must be less than, if I take the maximum value of this, which is m x into h k, it is definitely less than this product. I have taken the maximum value of this summation. I can put the summation, since this is a constant, summation sign here. So, y n, if this summation is denoted as sum h, I call it sum h, then it must be less than this product, all right. Therefore, sum h must be finite for magnitude of y n to be finite, to be less than a quantity, finite quantity. This to be bounded, that is, if this is to be less than equal to some m y, then m y must be less than m x into sum h. Therefore, sum h must be less than infinity. It must be a bounded quantity, it must be a finite quantity. Okay. So, this is the condition for stability of a system. You add up the magnitude of all the values of h n, it must be converging to some finite value. Now, let us take some standard functions and evaluate the Z transform. Standard functions or sequences rather. We have seen a into c to the power n, if you take the summation, will be a by 1 minus c z inverse, provided this magnitude is less than 1, is it not? This we saw last time, c to the power n, if you take the Z transform, the series that you get, this is a common ratio. So, that magnitude must be less than 1. If I differentiate with respect to the common quantity c, as we have done in case of Laplace transform, if we differentiate with respect to c, differentiate with respect to C, then I get a n c to the power n. Mind you, I am considering sequence for which exists for n greater than equal to 0, that is we are taking only causal sequences, okay. And I list out the corresponding region of convergence. So, a n into C n will give me n minus 1, thank you. If I differentiate, I will get a by 1 minus C z inverse whole squared into z to the power minus 1, okay. Minus 1 and minus 1, the final 2 minus 1 will give me plus. What will be the region of convergence? The same, C z inverse must be less than 1. If I put C equal to 1, what do you get? A into n will give me A into Z inverse by 1 minus Z inverse whole square. What is A into n? If you remember, what is A into n? A into n, it is basically ramp function. Moment I have defined n greater than or equal to 0, so all these functions should have their implied a un as a multiplier, alright. So, it is basically a ramp function. It is implied, though it is not mentioned, because I am taking only n greater than or equal to 0. So, A Z inverse by 1 minus Z inverse squared. Now, what are the regions of what is the region of convergence? I leave it to you to find out the condition when it becomes infinity. Okay. Similarly, A n squared u n try to check whether you get this. I can always multiply by z to the power minus 2, z to the power plus 2. So, this will become a z divided by z minus 1 whole square. Okay. In many books you will find they write in terms of z, alright, Z transform, and this becomes z minus 1 whole cubed. Derive it yourself, and again z greater than 1. Z inverse less than 1 means z greater than 1. Okay. If C is, once again we come back to the first relation involving C. Suppose C is equal to e to the power minus alpha plus j beta, then C to the power n means e to the power minus alpha n e to the power j beta n. Do you all agree? Now, what will be the Z transform of this sequence? So, A into e to the power minus alpha n into e to the power j beta n. You just put in place of C this quantity. So, it will be 1 by 1 minus e to the power minus alpha e to the power j beta into z to the power minus 1. Okay. I have just substituted for C e to the power minus alpha plus j beta. Now, if you segregate the real and imaginary part, what do you get? Let us see. Separating the, as we have done in case of Laplace transform, separating the real and imaginary parts and equating them on both sides, you get Z transform of e to the power minus alpha n cosine beta n as z squared minus z cosine beta by z squared minus twice zeta twice z e to the power minus alpha cos beta plus e to the power minus twice alpha. Okay. Some books write e to the power minus alpha as just r naught, okay, or r. So, you can do that because e to the minus alpha appears as it is. One may write also this as 1 minus z inverse cos beta. This is also written in many books in this form, e to the minus alpha cos beta plus e to the minus twice alpha z to the minus 2. Similarly, Z transform of e to the minus alpha n sin beta n will be z to the minus z to the minus 1 sin beta divided by the same denominator. Okay. We shall be using it later on in partial fractions in certain situations that we will see very soon. I will keep it aside. I would like you to try to find out the ROCs, determine xz and ROCs for the two functions xn equal to cos n and sin n, okay, alpha n, cos alpha n, sin alpha n, and second, prove that Z transform, you try this yourself, e to the power n, I am writing this C is basically A, okay, A cos n angle of P plus beta is C z by z minus P plus C star z by z minus P star, A, sorry, I have changed it to A, okay, to avoid confusion with the earlier C. Okay. So, A is a complex quantity, all right. Now, let us see how to you can evaluate the Z transform of many such functions by the same simple principle of addition. Now, let us see how you get the inverse of these functions. Given a function xz, how do you find out the sequence xn? That will be our next task. Inverse Z transform. Okay. So, there are three standard methods, very simple. Some of you must have studied in control systems also. Power series expansion, second one is partial fraction, and third one is residue method, residue calculation. Okay. So, the first one xz, suppose we give you xz as a0 plus a1 z inverse, like this, a polynomial am z to the power minus m divided by b0 plus b1 z inverse plus bn z to the power minus n. By long division, you generate this as x0 plus x1 z to the power minus 1 plus x2 z to the power minus 2 and so on. All right. You can divide it and then get this. For example, if I have 1 plus 2 z inverse plus z to the power minus 2 divided by 1 minus z inverse, say I have taken a simple quadratic z to the power minus 2, 0.3561 z to the power minus 2. What will be the sequence if x z is given by this ratio of two polynomials? What will be x n? It will be an infinite sequence. So, you divide it, take the denominator coefficients 1 minus 1 0.3561. I am not writing z to the power 0, z to the power minus 1, z to the power minus 2, just put a little gap in between the coefficients. Similarly, 1 2 1, 1 2 1. Okay. So, the division gives me 1 1 minus 1 0.3561. So, after subtraction I get 3.6439. Then next division gives me 3, then minus 3, 1.068, 3 into this much. So, that gives me 3.6436 and so on. Okay. So, next value will be 3.6436. Now, this is x0, this is x1, this is x2 and so on, because this is coming as a constant. What you are getting is 1 plus 3 z inverse plus this into z to the minus 2 and so on. So, this will be endless. So, will be this sequence. So, the coefficients of z inverse, z to the minus 2 and so on, they will represent x0, x1, x2 and so on. Okay. It is as simple as that. Recursively, you can write this as the same result. We can write x0 is basically a0 by b0. Okay. Sorry, it should be here. Okay. x1 will be a1 sorry b1 into x0 whole thing divided by b0. x2, I write one or two more terms and then a2 minus b1 into x1 minus b2 into x0 divided by b0. So, generalizing this, it will be xn equal to an minus I equal to 1 to n x n minus I b I by b0. So, you can use, I would request you to write a short program, take any polynomial a and b, az and bz, and then get the values of xn from this recursive relation. okay, maybe up to n is equal to 10 or 12. Write a short program and then see for yourself, give the coefficients and then find out the values. Okay. The next method is partial fraction. xz equal to a0 plus a1 z inverse etc. plus am z to the power minus m divided by b0 we took as bn z to the power minus n. If m is equal to n, then we can write, if m is equal to n, then we can write this as sum c0 plus c1 by 1 minus p1 z inverse plus c2 by 1 minus p2 z to the power minus 1 and so on, cn by 1 minus pn z to the power minus 1. Equal to, I can write this as a very general term, ck by 1 minus pk z to the power minus 1, okay, k varying from 1 to n. Now, from here, see, from the polynomial in the denominator we have evaluated the roots. So, the roots have to be evaluated here and then you can write in this form. For each one of them you know the solution. So, x n will consist of this sequence c k to the power n summation c k, okay, c k, c1, c2 etc. all to the power n u n. All right, and how do you evaluate c k? It will be x z by z into z minus p k evaluated at z is equal to p k, as you have calculated residues in case of Laplace transform. If x z has multiple roots, say m number of multiple roots, then that is, say x z contains a term like this di by z minus p k to the power I is varying to m, varying from 1 to m, okay. There is m number of roots are there at the same place p k. Then the corresponding residues, so if it is 1 by z minus say 0.5 to the power 3, then I will have a term say d1 by z minus 0.5 plus d2 by z minus z minus 0.5 squared plus d3 by z minus 0.5 cube. So, these di's, the general term di can be evaluated m minus I factorial sorry, excuse me, m minus I d z m minus I z minus p k, exactly identical method as you have done in case of Laplace transform. Okay. Let us take one or two small examples. Suppose x z is given as z inverse by 1 minus 0.25 z inverse minus 0.375 z to the power minus 2. I can evaluate the residues. This is factorizable, you can, this is a quadratic, you can find out the factors. Okay. So, 1 minus 0.75 z inverse, okay, let me write in the factored form first, 1 plus 0.5 z to the power minus 1. Okay. The factors are actually like this. So, this I write as A1 by 1 minus 0.75 z inverse plus A2 by 1 plus 0.5 z to the power minus 2. Okay. So, A1 and A2, one may try very simple combinations of 0.75 and 0.5. You can see A1 is equal to 0.8, A2 is minus 0.8. So, x z becomes 0.8 into 1 by 1 minus 0.75 z inverse minus 1 by 1 minus 0.5 z inverse. So, what will be x n? Very simple, 0.8, corresponding to this it is 0.75 to the power n minus 0.5 to the power n, whole thing multiplied by un. So, this is a close, this is minus 0.5, this was 1 plus 0.5, thank you, 1 plus 0.5 z inverse. Now, if Bz has a quadratic with complex roots, what will it do? If you remember in your earlier classes in Laplace transform, we studied the complex roots. If the denominator contains complex roots, then you try to resolve in say s plus alpha whole square plus beta square form, you remember, and we try to say if you are given some function as by bs, alright, and bs contains a factor like this, then you try to resolve it into some a into okay, some k1 into s plus alpha by s plus alpha whole squared plus beta square plus k2 times beta by s plus alpha whole square plus beta square, alright. Corresponding to this you get a cosine function as inverse, and for this you get a sine function. Exactly similar procedure we shall follow here. So, xz if it is given as az by bz and bz is having a quadratic, then we can write bz as 1 minus 2 into some e to the power minus alpha cos beta z inverse plus e to the power minus twice alpha z to the power minus 2. Okay. So, the quadratic that will be given to you, will tell you the last term z to the power minus 2, whatever is the coefficient, that will be corresponding to e to the power minus 2 alpha. Take the square root, you get e to the power minus alpha, then the middle term should be equal to 2 into e to the power minus alpha into cos beta. So, you know cos beta, okay. You can calculate sin beta also. So, this finally you reduce into the same form, some k1 times 1 minus z inverse cos beta e to the power minus alpha divided by the same denominator, plus k2 times z inverse sin beta e to the power minus alpha by 1 minus 2 e to the power minus alpha cos beta z to the power minus 1 plus e to the power minus 2 alpha z to the power minus 2. So, corresponding x n will be, after evaluating k 1 and k 2, it is just a matching that you have to do for the numerator function. So, you get k 1 times, what is the inverse of this, e to the power minus alpha cos beta. Okay. So, cos n beta, and this is minus alpha n, plus k 2 times e to the power minus alpha n sin n beta. Okay. So, that gives me k 1 into e to the power minus alpha, sorry, e to the power minus alpha n I can take out, k 1 into cos n beta plus k 2 into sin n beta. It is better to write in separate forms sin n beta and cosine n beta. Somebody may write cosine n beta plus theta, whatever you want. Okay. Now, sometimes we try to link up the discrete time Fourier transform, that is, if you remember earlier we were talking about frequency response of the system or frequency domain representation of a signal, that was x0 plus x1 e to the power minus j omega plus x2 e to the power minus j 2 omega and so on, is it not? If you remember, we are writing h e to the power j omega, frequency response of the system whose time domain response, impulse response was hn. So, this was h0 plus h1 e to the power minus j omega and so on. Okay. Now, you see in xz the expression is x0 plus x1 z to the power minus 1 and so on. So, from the Z transform you can directly get the frequency domain representation of the sequence, just put z is equal to e to the power j omega, you get the same function. So, in the Z domain, what is e to the power j omega? It is a unit circle as omega increases, omega increases along this e to the power j omega, omega is equal to say 2 radians, means I will go here by 2 radians. So, these are the points on the unit circle in the z plane. This is a z plane is a complex plane. Okay. That means some specific values of z which will be defined on this unit circle, if I take, then xz represents nothing but the discrete time Fourier transform of the sequence. We call it DTFT. This is known as DTFT, discrete time Fourier transform of a sequence xn. Is that all right? So, just take the unit circle, take the points on this, so that represents x e to the power j omega. Now, when I come back, that is when I complete 2 pi omega 2 pi, again I come back to the same point, same values. alright. So, I keep on making circles as omega tends to infinity from 0. If I keep on increasing the value of omega on the in the z plane on this circle, on this perimeter, I am just describing the same points, alright. It is one and the same thing. This is a point that we shall take up later on when we talk about stability of systems and well, in the filter design. As in case of continuous domain, you have varied along the imaginary axis of S plane, along the imaginary axis of S plane you have varied the frequency from minus infinity to plus infinity, or from 0 to infinity, even if you take 0 to infinity. Basically points on this represents different sinusoids or exponential periodic functions of this nature, is it not? You consider frequencies on the imaginary axis. We will try to establish a relation between S plane and Z plane parameters. That is, if I shift a point in the continuous domain along this, what does it mean in the Z plane? Rather, mapping of a particular zone in the S plane onto Z plane. That means, from the continuous domain, how to translate it into discrete domain. Is that all right? Thank you very much. We will continue with this in the next class.